You're the smallest audience in years. So let's make this an intimate. Yeah, so you can interrupt me or ask questions or whatever, since we are so few people here. Or it took me 10 minutes. And okay, it's just let's not talk about this hotel. Every time here's the same show. I can never find my way here. So just for the context of my presentation, I spent time at these companies here. None of them are really gaming companies. Yeah, so I was head of machine learning at Uber and GM for machine learning at Amazon. I did machine learning toolkit team at Microsoft, and I did work at IBM Research. The key point is that all these companies, they want to do AI, and as we'll talk about in a moment, working with real taxis and working with books and stuff like that, it's really hard to do what you call AI. Yeah? So let me just briefly, for those who don't know Unity, it's a game engine, but it's much more than that. We're strong in automotive, we're strong in film as well, and the key point is this idea of real-time 3D. Yeah? So when Pixar makes a movie, or Disney makes a movie, they render for minutes and they get one frame. Our job is to render at 30 hertz or 60 hertz, and in some cases I will show you at much higher rates. Yeah? 60% of games on 4 billion devices. It's fun for me to ask people if they ever tried Uber or they shop at Amazon, they heard about Microsoft. Yes, everybody, 100%. And then Unity, and there'll be like one guy saying, I think I know what it is. But it's on your phone. It's almost, I think it's about 40% of the App Store on iOS is actually Unity bits, which is kind of interesting. Yeah. So these things here, that all the companies I showed you and a few other companies, they work on, except, actually, we saved that one. In my opinion, not a lot about AI. Yeah? This is really about really smart software engineers and mathematicians writing some really smart algorithms that does something, yeah? But it's thought out by people. I worked 8 years in 2 startups on virtual assistants. One became OnStar from General Motors, and the other one was acquired by Google for their speech services. Siri and Alexa are built the exact same way as we did in 98, 99. Yeah? Handcrafted at large scale. Yeah? Domains, you get into the stock domain, you can only talk about stock, you can't talk about other things, pre-canned jokes, all that kind of stuff. Just people did it, yeah? So there's no AI really anywhere here. There's a little machine learning, there's deep learning and speech recognition, but that's not AI. That's just engineering, yeah? And this, of course, is the funny thing, which all the AI titles on LinkedIn, yeah? Okay, so what is it really, yeah? And if we look about, we take up the dictionary, we get something there, but again, that's pretty abstract to me. So what is the only real AI we know, yeah? Sorry, not the A, but the I. The real intelligence we know, that's the thing in biological systems, yeah? So it's stuff we need to do because of 5 principles. Number 1, we need to consume energy to maintain life, yeah? So the intelligence we see around us, including our own and animals and a lot of stuff around us, is really about consuming energy while not being turned into energy yourself. Yeah? That's really the core of it. Then procreation, because we don't live forever. And then physics, watch out. Yeah? Don't fall down, because that's going to hurt. Yeah? And there's agency, this ability to interact with your environment to improve your survivability. Yeah? If you want what we know as life in its broadest form, it's really all about this. Yeah? This is evolution, and what evolution did is it created all this stuff here that you see on the slide to enable intelligence. Yeah, so it created an infrastructure. So bunch of things. Yeah. I need to get the clicker going here. Stuff, all this stuff. Like we didn't always have eyes. Yeah, eyes came around 450 million years ago in a very short time span of maybe 300,000-400,000 years. There were no eyes, and then there were eyes. Yeah, because it was advantageous to see. Yeah, it's advantageous to feel touch, have hearing, taste, smell, all that stuff. Yeah. Actually, if you start looking at what kind of sensors animals have, there are many, many more, like magnetic ones. Yeah. We also have the sense of balance. It's a special one. Yeah, to keep us standing up. Yeah. We have tons and tons of sensors. Yeah, that we don't think about, and all these things are invented to enable intelligence. Yeah. So, having said that, let's get back to the game engine. Yeah. The game engine has all that. Yeah. If you think about the game engine, it has 3 dimensions, has time, has physics, has in an enclosure, it has everything you need to play around with the elements, the core elements that led to intelligence. Yeah. So we built a toolkit to have lots of people being able to do that. And in my talk here, you should take as contrast to me building a recommendation algorithm for Amazon or building some algorithm that gets an Uber vehicle faster to you or make a better ETA, whatever. All that stuff, it's sort of software engineering. Yeah. This stuff here is much more different. Yeah. This is all about self-learning systems. Yeah. So I'm gonna get into that now. So games, yeah, have all kinds of weird stuff in there, just like the real world has all kinds of weird stuff in. Yeah. So one of our biggest partners is actually DeepMind. DeepMind is doing a lot of stuff on Unity. We work very closely with them to make Unity their engine of experimentation. And do anyone know what DeepMind they want to do? They want to create artificial general intelligence. Yeah. And how do you do that? You basically create environments. Yeah. So what is it that nature has given us then? And well, in a very general sense, has given us reinforcement learning as its core. Yeah. That you observe around you, you take some action based on your observation, and you reap the rewards or the penalties from that. That's how almost everything around us operate. Yeah. That's how kids operate, that's how we operate, that's how animals operate, that's how a lot of nature operates, and you can expand it a bit into evolution itself if you sort of blend learning with evolution. This is basically about trying stuff. Yeah? And what happens is that you move from explore to exploit. You move from learn through the learning process, you move from not having a clue to actually start to understand. Yeah? So let me give some examples. Everything I show you today is tabula rasa, clean slate. There's nobody here hinting at the system how to solve a task. It's learning it purely accidentally from trying and trying. Just like a dog actually figures out that it does something, it gets a piece of food from you, and it does something else, and you kick it, yeah? Something like that, yeah? So it figures out that if I do this kind of stuff, it's good, and if I do this other kind of stuff, I get kicked, so I don't do that. That's how dogs learn, yeah? You can't tell them, like what you want, yeah? They just have to figure it out, yeah? Okay, this is computers learning that way, yeah? We were wondering whether we could get the yellow chicken, to cross the road safely while picking up gift packages and avoiding the cars, yeah? It can do 4 things: left, right, forward, backward. A computer sees the pixels, that's it. I'm not cheating, just see the pixels, 80 by 80 actually, so you see a much higher resolution than it sees. And there's a reward signal. We basically say bang every time the chicken gets hit and killed. That's a negative. And every time it picks up a gift package, we tells that a positive, yeah? That's it, yeah? And look, we'll let it train. And initially, it's really just moving more backwards than forwards. It doesn't really know where to go because it knows nothing at this point. But watch that gift package up there on the right. Boom, and then the car. 10 seconds, 2 bits of information. Gift packages are good. Cars are not so good. After an hour, it gets pretty good at it. It tries over and over for an hour, and we come back and we see this. It gets good at collecting packages, and it gets somewhat good at avoiding the cars. Not perfect. And look, it's doing a lot of interesting things by, moving backwards a bit to pick up a package, waiting for cars to pass. It's doing a lot of interesting stuff. Now, watch what happened here. After 6 hours of training, it became superhuman, yeah? It's just killing it. And these cars are coming in randomly. Never seen it before in this configuration, yeah? Every moment here is a new and randomized moment, yeah? Non-deterministic, yeah? But it tried enough to figure out what success means and how to get there, yeah? So I'm going to show you a lot of scenarios that are based on this principle. Control learning, that is, moving stuff. So here we have some spiders, 4 legs, 8 joints. Yeah? So imagine the programming here, 8 joints. I need to write some Java or C# or C++ program or Python, you name it, that tells which joint to move when and how much. Yeah? Or I just let the spider wiggle around for an hour and through trial and error figures out how to move 4 legs, 8 joints in some pattern, moving from left to right. Yeah. Or this, anyone who had small kids, 9, 10 months old, please try to see if you can stand up and everything, goes for a few seconds and then they fall, yeah. There's a lot of joints here that needs synchronization, yeah, to keep standing. Again, computer can learn it. Or what about this? I give it a humanoid, some kind of geometry similar to ours, not perfect. And I try this over and over and over. They always end up going that way. So I will conclude that the way we walk around is probably the optimal way of walking around if you have our geometry. Yeah. These guys could have been jumping, they could have been going backwards, they couldn't be doing anything. I never told them how to solve the problem. Another fun one here. Look at this guy. He needs to scale the wall, but the wall is too tall sometimes, so he actually learns to use the orange cube as a stepping stone. And if it's not right next to the wall, I will move it next to the wall. Learns that from scratch. Yeah? Very complex task. And if you notice in some of the examples, it will just actually, I think there's an example where it skips the, yeah, there it skips. Because if the wall is low enough, I don't need a stepping stone. So why bother moving it over there? This is very, just think about this from scratch. You figure out, the system figures out to use a tool. Yeah? It needs to figure out that it can push things around, actually. Yeah? It needs to learn that, I can push stuff. It doesn't know that. It doesn't know anything. Yeah? So after 1 million attempts, it figures this out. Yeah? How does this happen? Well, we found an interesting thing here, which is this particular example is best learned if we start easy. So we let the wall be low. And then we make the wall incrementally taller. We wait for it to be really good at scaling the wall, and then we raise it a bit, and raise it a bit, and raise it a bit. And it needs to graduate before we raise it, yeah? So it needs to be good at that level, and then we raise it, yeah? What happens is this interesting graph, the blue one, that by going through a curriculum and make it harder every time you're good at a given level, it learns faster. You can see the height of the graph, the blue graph, the height is how good it is, yeah? And time goes out here. So it gets actually pretty good very fast, yeah? The orange one is where we basically just let it start out at the most complex challenge. Yeah? And it takes a long time to learn, and after a given time, it's still not really good at it. And why is that? Well, that is actually at its core is the mechanism that's behind us going to school, going through first grade and second grade or third grade. Jumping right into high school, not a good idea. Why not? Not because we can't learn it, but we're going to learn more chaos than structure. Yeah? What happens here is that you actually build structure up from easy to harder and harder, and you build structure up, and the structure gets refined. Yeah? So memory is another one. You need to, depending on the color of the cube, if the cube is orange, orange exit, if it's red, red exit, gets really good at this. We actually never tell it. It's the color that matters. We just basically say good or bad. And after a long time here means, I don't know, 30 minutes, an hour of training, it figures out that it's actually the color that matters, not the size, not the position. It could be anything that mattered, yeah? It tries to understand the relationship. It learns that too. Kind of interesting if you're a software engineer here, because it's one of these kind of, that used to be our job. Like read the color, determine the exit, yeah? Here, we don't even tell it. It just figures it out, yeah? This is another one that's interesting. We reuse the model that controls the spider legs, but then we add another model in there which basically says where the target is. Turn right, 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 left, straight, right, left. Yeah. So what you have here is a What you have here is a hierarchical model where one takes care of navigation and one takes care of the motor system. Yeah. This is how we work too. Yeah. Only penalty here is if the ball touches the ground. So they get really quick at playing together. Yeah. Another one is soccer. We made an offensive player, defensive player, and then we put them together. So one player is rewarded for scoring. One player is penalized for having goals being scored on them. Yeah. Put them together, train them together so that they can make each other better. Yeah. And then we copy them into two teams, and it looks like this. Yeah. The funny thing is that if I tell you protect the goal, prevent scoring, apparently you become a goalie. I didn't ask it to create a goalie. I just said, you have a defender and you have a striker. Strikers are also funny because look, the little white thing is an eye. They run sideways. Why do they run sideways? Because when you look sideways, you have the whole field of view. So up along the line, sideways, and you see everything. This is actually what soccer players do too. Yeah. They like to go up along the side because there you only have to worry about what's to your left. To the right is only the parents yelling, yeah, so you can ignore that. Another example where we make it a little harder, the Asians can kick the ball, but there's a penalty by kicking the ball. When you kick the ball, you freeze to ice for 2 seconds. Yeah? And I will show you an individual reward system. Yeah? This is where a particularly Asian gets rewarded for scoring a goal. And it looks like this. They sort of kick the ball, but when they get close to the goal, they get very reluctant kicking. If you see, they're just dancing around the ball, because what happens if I kick the ball, then I freeze to ice for 2 seconds, and someone else may grab the ball and score, so I don't get the reward. So I don't want to kick first. Yeah. So they stop working together. It's just like certain companies where there would be individual rewards to the team members, and then you don't see any collaboration at all. Yeah, yeah. No names mentioned. In this case, we make it harder. We tilt. We incline the field, and what you see is that because it freezes to ice all the time, it can't do the work. Yeah. So what we do is that we add a couple of other guys in there, and we tell them as a team, score. And they developed this collaboration. I didn't tell them to play this way. They just figured it out, yeah? So they help each other to score, yeah? Which is interesting. We'll get back to that in a moment, yeah? So let's talk a bit about types of rewards. We have shown you a lot of rewards where it's getting rich rewards, yeah? It's extrinsic rewards, I collect something, yeah? But there are other kinds of rewards in life. nature gave us all these other rewards, yeah? We call them traits, like curiosity, impatience, happiness, love, empathy. I can go on, yeah? You can go on Wikipedia. People can decide whether we have 12 or 72 or 34, whatever. There's a lot of disagreement about these traits, yeah? Why did nature give us traits? Well, they're specific to the agent. They're inside our heads, yeah? We are happy or we are not happy because it helps survivability. We have empathy. We are good, concerned about other people. Apparently, that's really good for our species, yeah? Sometimes we are not concerned about other people. Apparently, that's good for our species too, yeah? So we must be able to use that to solve certain problems that standard reinforcement learning will not solve. And I talk about long events chains, long complicated chains of events where it's not just about crossing the road any longer while not being hit by a car. It's much more complex, yeah? And we have found that the solution to solving these more complex problems is to go from sort of random exploration to use certain strategies. And one thing we did was that we basically put curiosity into math, and the magic is here. It's the minus log. The minus log is sort of normally in machine learning, you want to minimize error. What we're doing here is we're training to maximize error. We're basically teaching the agent to see where it will make the biggest mistakes, yeah? Because it's only when you seek out the biggest mistakes that you learn something really new, yeah? And in practice, this is an example. The agent here enters a house with a lot of rooms. It needs to find a push button, push the push button. A pyramid is created with a gold bar, and it needs to knock down the pyramid to get the gold bar. That's the extrinsic reward. Random exploration is an agent that is entirely uninterested in anything, yeah? It's just moving a little forward, backward, sideways, and it keeps going like that, yeah? That's how most recommendation systems work out there, yeah? They just start out by being total random, yeah? Let's throw curiosity in here, yeah? But no extrinsic rewards, so it's not trying to get rich. It's just curious, and look how it goes from room to room. And it now realized that if I hit a pyramid, something happens. I move things, look. And then let me get more speed on and see what you see? It systematically tries to figure out how to learn more, yeah? Then let's put this together with the goal of getting rich. I'm curious and I want to be rich. And it looks like this. It goes very systematically from room to room, looking for something like the push button, hit it. Let's find something else that happened. There's the pyramid with the gold bar. Now go and get the gold bar. Boom, done. Yeah? It's very systematic. It's not wasting time. Yeah? It's not exploring the floor. It's not exploring walls. I've seen lots of walls. Walls are not interesting. Yeah? They're not surprising any longer. Yeah? So it's looking for surprises. Yeah? There's something we call the TV trap. So if I put a TV in there, this agent is very curious. I put a TV in there, the agent gets in front of the TV and stops and gets stuck. TV trap. It's actually an academic term now. We call it the TV trap. Agent is curious. TVs allow you to see stuff you've never seen before forever. Yeah? Terrible. So it tells you that you can't live by curiosity alone. We need to have something else too. Yeah? Let me show you Popo. Popo is a virtual robot. It has to learn everything, just like the spider. There's no animator here, there's no coding. It's basically physics and 3D and reinforcement learning, and a rewards function, always a reward. We have to have a reward, yeah? Almost always have to have a reward. Fetch the stick. Yeah? We'll send Popo in training camp, and you see Popo is not very good at walking. I mean, like it's 4 legs, grab the stick, all that stuff, yeah? It's tough, but after a little training, it looks like this. I throw the stick with the mouse, zoom, and Papa will go and fetch it. This is not hand-coded, yeah? This is machine-learned animation and behavior, yeah? Brings back the stick, because that's the reward, yeah? And whoop-chee. Yeah? So this is machine learning in action, where you have this feedback loop, yeah? Another example, fetch the bone. and it runs to fetch the bone, yeah? And then I have 10 of you, so now 10 individual learned systems are now fighting to get to the bone. You can see they actually push each other over and stuff like that, yeah? Yeah. This is not a swarm function. This is not a mathematical representation of a group of dogs. This is actually each dog here physically fighting for space. And look at these guys on the grass. Yeah, they're cutting over on the grass. Yeah, shortcut. That's very beneficial apparently. Yeah. Anyway, so everything I showed you, by the way, is on GitHub, so it's all open source to be used with the Unity toolkit. I also want to show you this. This is a video game we made, but it's just for computers to play. Yeah. And it's basically a tower of challenges. And we're actually in a competition. It's really intended to make it really, really hard for machines to do. Yeah. There's 100 levels in the tower. Right now, the leading contestant is at level 19 of the 100. Humans can play. I can't play to level 19, but some people can play to level 22. So humans are still slightly better than machine on this one, but it's not going to last long. So you can check it out. It's called the Obstacle Tower Challenge. Yeah. You see, I read biology I read at least one paper a week from the biology world. Everything I showed you here, we're cheating, yeah? We're looking nature over the shoulder and cheating, yeah? But what I want to alert you to on my last slide is this, which is culture, not biology, yeah? It's the idea that humans evolved over 200,000 to 300,000 years. 100,000 years ago, tried to migrate out of Africa, failed, tried again a little later, and made it all the way to Australia, yeah? So something happened. We talk about the cognitive revolution, yeah? This figure out here is 32,000 years old, yeah? So someone created a human body with a lion head, meaning that they had imagination at that time, yeah? What I want to emphasize is that the human brain had no Moore's law, yeah? Okay? In 70,000 years, there's been no changes to the processor whatsoever. Genetically, no changes, yeah? So in 70,000 years, we went from picking berries to putting people on the moon. So what happened? Well, this happened, yeah? We learned a lot of stuff about working together, yeah? We understood emergence, language, collaboration, anticipation, yeah? So I showed you all these small examples of agents doing stuff. What I want to leave you with is, well, next time someone says I need a new upgrade for my NVIDIA card so my GPU can be faster so I can do more machine learning, well, maybe you just need more of them, yeah? And they have to figure out how to work together, yeah?